so far in this course we have seen how one can write the network equations for an LPTV network. And this basically involved creating a conductance matrix where each entry is now a matrix in itself, and that contains the Fourier coefficients of the time varying element. Now, we also saw how one can determine special cases where one can determine h sub minus L of j 2 pi L times f or L times Fs, and this was a special case where the output frequency is DC, and we said that we could find this by exciting the LPTV system with a cosine, exciting with a sine, and then just simply looking at the average parts of the waveform. Now, today let us continue on with some other properties of LPTV networks. I would especially like to highlight the fact that things that we are very familiar with when we talk about time invariant networks will not necessarily be true when you have a network with periodically time varying components. And one example is the following. We know that if you had a time invariant network, this was LTI, then, and let us say the network had no sources inside, then if you excite the network with a current e to the j 2 pi f t, the voltage developed is say V, the phasor V, then we know that the impedance Z of j 2 pi f is simply nothing but V by I. Technically speaking, this must be if I is the phasor, then what you are exciting the network with is I times e to the j 2 pi f t. The voltage that is developed is V e to the j 2 pi f t, where V is the voltage phasor, and the impedance is simply nothing but Z of j 2 pi f. Now, if on the other hand we took the same LTI network and excited it with a voltage phasor V, meaning that the waveform is V e to the j 2 pi f t, then it will turn out that the current will be I e to the j 2 pi f t, and the ratio of the current developed to the voltage developed is nothing but I by V. And for an LPTV LTI system, Z of j 2 pi f is simply 1 over Y of j 2 pi f. This is of course very well known from our earlier classes. In other words, it does not matter in an LTI network if you want to find the admittance. It does not matter whether you apply a voltage and measure the current, or you apply a current and measure the voltage, and the impedance is simply what do you call the reciprocal of the admittance. Now, Well, it turns out that that's definitely not the case, not necessarily the case when you deal with periodically time varying networks, and we will spend a little bit of time trying to understand why that is so. Before we go there, let's basically prove this for an LTI network, and then we use the same way of proving, we use the same method to go and analyze an LPTV network and see where that leads us. So, in other words, we would like to understand why in a linear time invariant network the impedance and the admittance are reciprocals of each other. So, let us say we excite this with e to the j 2 pi f t a current, and this voltage V is developed, right. This is LTI. Now, what I am going to do is replace the, what I am going to do is the following. I am going to, we know that V is nothing but Z of j 2 pi f times 1 angle 0, right, because this is the phasor corresponding to the current excitation. Now, this is a network and this voltage here is this phasor V. Now, the network would not know if I replaced the current source with the voltage source with, which is Z of j 2 pi f times 1 angle 0, right. The current that would flow there, the current phasor that would flow there would still be 1 angle 0, right, because as far as the network is concerned, it would not know the difference whether it is being driven by a voltage or if it is being driven by a current, right. So, this is often what is called the substitution theorem. All right. And now, the next thing I am going to do is basically use linearity. If you know that this is a linear network after all. So, if I scale the strength of the source by a number, then the response will also change by the same factor, and therefore, what I do next is by linearity. So, scale the source by 1 by Z of j 2 pi f, right, and therefore, this would be 1 angle 0 divided by Z of j 2 pi f, right. So, this so by linearity current must be right. So, but by definition the admittance y j 2 pi f is simply the ratio of the current to that is, which is basically this is the current that flows into the network when it is excited by a voltage. right, and that is basically as we see in this picture, all right. And as you can see, this is simply nothing but 1 over z of j 2 pi f, all right. So, the admittance is simply the reciprocal of the impedance, which is something that we knew already. There is nothing new here. Now, let us try and see where if we try working the same way with an LPTV network, let us see where things lead us. So, let us assume now that we are working with an LPTV network. It is varying at Fs. We will excite the network with a current e to the j 2 pi f t, like we did in the time invariant case. Now, the voltage developed here is because of time variance, not merely consists of stuff at frequency f, it will also consist of it consists of all tones of the form sigma L, I do not remember if you kept using L or K, let us use K, sigma K, V sub K e to the j 2 pi f plus K F S times T, all right. So, that is the voltage V of t developed there, right, and the current of course is e to the j 2 pi f t. Now, like we did in the time invariant case, we are going to, oh by the way, V of 0 divided by 1 angle 0 is the ratio of the strength of the voltage at f to the current at f, and that is simply, that is by definition the z 0 of j 2 pi f. Now, let us see what happens when we now replace the current source with a voltage source by the substitution theorem. What do we need to do? We need to replace, if you want the current here to remain e to the j 2 pi f t, what you need is you simply cannot put just V 0 e to the j 2 pi f t, you need to add all the components. So, basically what you need to do therefore is to add this voltage source has to be V of t, and that remember is simply has to be not merely V 0, but you must have all the other components that are present in V of t. Right. Now, the next thing is that we will scale. So, remember that V 0 is z naught of j 2 pi f, right. Now, what we are going to do, this is the substitution theorem. Next, we are going to resort to using linearity. So, this is LPTV at Fs again. Now, I am going to scale this by z naught. So, we will call this is now e to the j 2 pi f t plus sum over all k, k not equal to 0, v k over v 0 e to the j 2 pi f plus k f s times t, all right. And the current that flows through here will therefore be e to the j 2 pi f t divided by z naught of j 2 pi f. So, this is by linearity, right. Okay. So, the key point to notice is that if you wanted to measure admittance, what you would have to do would be, or what you tend to do would be to excite this with a voltage 1 angle 0, right, which is equivalent to saying that I will put in a voltage of e to the j 2 pi f t, and the current that would flow here, you would that would be y 0 of j 2 pi f plus a whole bunch of other terms, which I will actually write down here. So, y 0 of j 2 pi f the j 2 pi f t plus sum of k not equal to 0 y sub k e to the j 2 pi f plus k f s times t, all right. So, what this is saying is that clearly if you simply excite the voltage the network with a voltage e to the j 2 pi f t, the current y 0 of j 2 pi f times e to the j 2 pi f t, which is basically the admittance seen at the frequency f, right, is not 1 over z naught, because for the current to be 1 over z naught times e to the j 2 pi f t, it is not merely enough to add or to excite the network with e to the j 2 pi f t, it needs all these extra components, right, because since the network is LPTV, right, these components are all getting either down converted or up converted by appropriate amounts, and then they all add up, and that is how the current becomes simply 1 over z naught, right. So, it is therefore, y naught of j 2 pi f is not necessarily equal to 1 over z naught of j 2 pi f. Okay. So, let us take a simple example to prove the point. Here is a voltage source, let us say it is a DC voltage, and we have a capacitor C, and when this clock waveform phi 1 is high, so phi 1 looks like this, and phi 2 looks like this. Okay. and the let us take a look at the impedance looking in at DC. So, as you can see, so if you look at during phi 1, the capacitor C is charged to 1 volt. During phi 2, the capacitor is completely discharged. So, if you look at this current I of t, it basically assuming the switches are ideal, the current I of t basically is an impulse at every rising edge of phi 1. Okay. And the charge contained in this impulse is C times 1 volt. Okay. And if the frequency of operation of these switches is Fs, then the average current is just simply C times 1 volt times Fs, right. So, the DC impedance or DC admittance actually is 1 volt divided by the average value of the current that is flowing, okay, and that is simply 1 over Fs times C. So, for those of you who have seen this before, this is nothing but a switched capacitor resistor. All right. Now, the next thing that we would like to do is, so in other words, the low frequency admittance is 1 over Fs times C. Now, let us see if the same network is driven by a current source, and let us now measure the impedance and see what that amounts to. So, you can see that clearly when when phi 1 is high, the voltage across the capacitor becomes infinite, right, or rather it keeps going up as a ramp. Voltage across the current source is a ramp. Well, when phi 1 is low, well, the voltage is infinite, right. So, the average voltage therefore, if I look at this voltage V of t, is simply infinity, right. So, Z therefore, of j 2 pi 0, that is the DC value of the impedance, is infinity, which is definitely not the same as 1 over y of j 2 pi 0. Remember, this we calculated to be 1 over Fs times C. Okay. So, familiar things like impedance and admittance are inverses of each other, etcetera, do not necessarily work with LPTV circuits.